we'll explore more about zeros of polynomials and how to find them. So two of the main aspects are in this section are long division of polynomials, or sometimes we can use synthetic division of polynomials if we have a linear factor that we're dividing by, say like x minus 2, and it has one root. Otherwise you have to do each one individually, maybe factor it down to the linear factors. But synthetic division is basically, it mirrors the long division, but it's a little bit quicker. It's sort of like a shortcut. So just like with fractions, if degree of the top is smaller than the degree of the bottom, then we have a proper rational function, and it's like a fraction we cannot divide. It's like 3/5. That's the best you can do. But if the degree of the top is equal to or greater than the bottom, then we have an improper fraction and we can divide. It's just like, let's say, 5/3. So you can do the division. You may have remainder, but you can still do it. So we can either do, let's say we're trying to divide the polynomial x cubed plus 2x squared minus 1 by x minus 2. Let's first take a look at the long division, like how does the process work, and then we'll compare it with the synthetic division. So how do we do this? And again, I have it all written out or typed out so that way it's easier to follow, but let's do this step by step. So typically how I do it, I focus on the leading term, which is x cubed, and then the leading term for x minus 2 right here. Let me get the pencil going. Okay, so let's say x goes into x cubed, we can multiply by x squared. And if we do, here is the x squared, we multiply it, we distribute it, so we get x squared minus, we get x cubed minus 2x squared. And what we want to do is we want to subtract the whole polynomial. So x cubed cancels, which is what we want to do, like that. And we can subtract, but when we do subtract, the minus and negative actually becomes positive. So what I usually do, I circle the correct sign, so that way I remind myself to use the switch sign, the circled one. So it should be 2x squared. They actually do not cancel out. It should be plus 2x squared, so we'll get 4x squared. And we'll repeat the process with the leading term here. So x goes into 4x squared 4 times, actually 4x times. So that's why we have the 4x here. And once again, we need to multiply the 4x by the x minus 2, just like it says on the side right here, and distribute it. So we get 4x squared minus 8x. Same kind of idea. We subtract. It's kind of easy to remember. So this one cancels, but you're left with because we did not have x in the original problem, if you notice it was missing, what you do want to do, so you don't have anything left over, you do want to write in 0x for that the constant. So you want to have every degree accounted for. So the plus 0x basically comes down. Okay, we just copy it down. And again, same idea, we subtract, but minus and negative becomes positive again, so we'll get 8x. So this time, x goes into 8x 8 times. Here is the 8. Once again, we multiply. So we'll get 8x minus 16, and again, we subtract, and it becomes positive against a negative 1 plus 16 is 15. Now, x cannot go into 15. As soon as we get to the degree that's smaller, like 15 here is a constant versus x, then we know we have a remainder. And here's the answer, x squared plus 4x plus 8 with remainder 15. But of course, like any long division, it does take time a little bit. Once you get used to the process, you do want to check it. It's a little bit hard to check, but we'll actually see in this section there is an easy way to check whether you got this right. So, but that's how the process works. Now let's see how it would work with synthetic division. So the first thing we need to do is find the root of x minus 2, basically set it equal to 0, and that gives us x equals 2. So which x makes it 0, the linear factor that we're dividing by? So it's 2. Good. So we write 2 on the side like this. It's a little bit hard to type it with a computer, but it's basically, it's isolated. That's what we're dividing by. Now we write the coefficients of the original polynomial. If we recall, it was x cubed plus 2x squared minus 1. So we have 1x cubed plus 2x squared plus 0x, if you recall, and then the minus 1. So it kind of works similarly. We're just writing the coefficients. So the way synthetic division works, we copy the first coefficient down exactly as is. Then we multiply by the 0. 2 times 1 becomes positive 2. And we add the coefficients. I guess this is instead of subtracting and remembering to change the sign, you're just adding the coefficients. And that's why we're finding the 0. That takes care of changing the sign, because it was originally x minus 2, but that's why we find the number that makes it 0. So basically we add them. So 2 plus 2 is 4. Again, we multiply by the 0. 4 times 2 is 8. That's how we get this number. And then we add them, we get 8. So we multiply, we get 16. And again, we're kind of mirroring from the long division. You see, again, just without changing the sign. We just keep adding. And notice how we get a similar answer. Now, how do we translate back? I usually read it backwards until you get used to it, and then you start noticing, here's how I would write it. So here's remainder is 15, that's the last number. And then you kind of read it off. You start with a constant, so it's 8. Then you increase by 1 degree, then plus 4x, then plus x squared. So you can write it like this in the ascending order. And then, of course, you can rewrite it in descending order, which becomes x squared plus 4x plus 8. So that's the easiest way to remember, unless you can remember to decrease the degree by 1, or, there's other several tricks. But the easiest way is to basically work backwards in the ascending order and then switch it up if you need to. Now, it's fairly easy to check the answer to see if you did it correctly. And here is the 2 new theorems that we're going to learn in this section, the remainder theorem and the factor theorem. So what does the remainder theorem says? So if you divide your polynomial by a linear factor, x minus a constant, we'll call it a, then the remainder is, if you plug in that value into the polynomial, f of a, the result you get is the remainder. See how easy it is to check. How did we know if we did this right? Remember how remainder was 15? The number that we divided by, remember it's 2, because we're subtract x minus 2. Let's plug in 2 into the polynomial. And we get 2 cubed plus 2 times 2 squared minus 1. So we'll get 8 plus another 8, and then minus 1, we do get 15. And we did it right. Yay for us. So it's kind of nice, especially if you're working quickly with synthetic division or long division. You do want to know if you did this correctly. Now, factor theorem kind of follows from the remainder theorem. If you do not have a remainder, that means the division is even, just like with numbers. And of course, if you don't have a remainder, then x minus a is a factor. That means originally we could factor the polynomial. So it's kind of an important one. Pardon my if you hear the noise from the outside. It's a little bit noisy today. Anyway, so that would help us. Okay, again, we can quickly check whether it's a factor and if we get a 0 remainder. So now the main portion of this section is the rational zeros test. Now this is useful for higher degree polynomials, and let's say you don't know how to factor it exactly. Sometimes it's possible, sometimes it's difficult, sometimes it's not possible, because you know how you may have fractions and so on, or maybe even just real numbers. Maybe you don't even have rational numbers. So rational zeros test basically gives us some possibilities to get started with. And it's like, when you're trying to unravel maybe, I don't know, a ball of yarn or something like that. As long as you get the string, the rest is easy. You can just follow the string and get the rest of it. It's kind of like with the zeros the same way. Once you get the first one, then you can use the division, the synthetic division or long division, and you can find the rest of them. Or maybe you can figure out how to factor it. But once you get one of them, then you're kind of on your way. So this is what the rational zeros test helps us figure out. What are the possible zeros? Now keep in mind, these are possible zeros. They may not be the actual zeros. They may not work at all. But if it does work, then it may possibly be 0. So here's how it works. Let's say you have a polynomial written in general form like this. And let's say this fraction p over q is a 0. Then the following is true, that the numerator is a factor of a constant term, just kind of handy to know, and the denominator is a factor of the leading coefficient. right here. So this is what we use to generate the zero. So here's kind of the idea, the way it works. Let's start with find the set of all possible zeros. You have this polynomial. First, you may want to figure out the constant term, that's 6, we'll denote as A0. The leading coefficient, since it's degree 3, I'm going to call it A3, is 4. Now, first you want to do, find your P and the Q. So your P, the numerator, should be the factors of 6. Now keep in mind they're up to the sign. They could be negative because the two negatives would multiply the positive 6. So plus or minus 1, plus or minus 2, plus or minus 3, or plus or minus 6 would work. I'm writing plus or minus in the beginning, but keep in mind it's up to negative because again, negative 1 times negative 6 would give us positive. So these are all the factors. So 6 usually has a lot of them. 4 has a little bit fewer, so it's plus or minus 1, plus or minus 2, plus or minus 4. Then how do we write possible zeros? First, I'll kind of walk you through the pattern and then we'll learn how to simplify them. The first thing, since 1 is always a factor in the denominator, then we first get the integers. Typically, I usually write them out 1, 2, 3, 6. So they're all over 1. And then again, they could be positive or negative. So again, I'm just doing one denominator at a time. So first they're all over 1. They're going to be our integer possible zeros. It's nice when your 0 is an integer. But of course, could be a fraction, but we always start with integers because they're easier. Same thing, the next is every single one of them is over 2. 1, 2, and 3, and 6. Then, every single one of them is over 4. Now, keep in mind there's going to be some redundancies, and as you get faster at this, you're going to eliminate them quickly. So how do we eliminate them? So let's take a look. First of all, the 1s over 1 are simply the integers. Notice how you have 1, 2, 3, and 6. The 1s over 2, let's see which ones reduce. Like 1/2 does not reduce, so we do have it. Okay. 2 over 2 does reduce to 1, which we already have, so we don't need it again. We get rid of it. 3 over 2, which we have over here. Maybe I'm just, it doesn't matter how you list them. You could list 3 over 2 first. And then 6 over 2 becomes 3, so we get rid of it. Then we have 1 over 4. 2 over 4 becomes 1/2, which we already have. 3 over 4 stays, which is right here. And 6 over 4 becomes 3/2, which we already have. So again, does not matter in which order you write them as long as you get all of them. All right. And that's how you can reduce them. So basically, if you see the even ones, the ones that reduce, you can get rid of them. So again, as you get faster at this, you'll see it right away. You don't even have to write the long version. But that's a good way to get started. So now let's take a look. How do we use this? So here's an idea. We want to find all rational zeros of the given polynomial. So once again, we have the 6 as the leading coefficient, the 2 is a constant. 2 is a little bit easier, but 6 can give us a lot of answers. So first, maybe pause this video and see if you can find possible rational zeros. So write out all the P and the Q and all the possibilities. Okay, the 2 would only have plus or minus 1 or 2, but then you're also going to be dividing by 6, 3, 2, and 1. Okay, now pause this video. Hopefully you had a chance to come back, and here's what we get. Positive or negative 2, positive or negative 1 over 6. So again, I'm writing plus or minus in the very beginning. It basically implies they all could be positive or negative. So 1 over 6 gives us 1 over 3, 1 over 2. So a lot with the 1s, because with the 2 they would be reduced. And then 2 over 3 is the one that does not reduce. So that's a lot of possibilities to check, because remember, we're actually trying to find all rational zeros, and not just the possible ones, but what are the actual rational zeros. And this is without graphing or doing anything technologically, at least not yet. So how do we go through this? Once you get your possible zeros, it's like getting your foot in the door. Then the quickest way, you can start with synthetic division, but sometimes it can take a while unless you get lucky. So here's what I did. I started plugging them into the polynomial. I plugged in 1, I get 18, not a 0. I plugged in negative 1, I get 4, not a 0. So unfortunately, 1 and negative 1 are not zeros. Plugged in 2, get 100, not a 0. Plug in negative 2, and finally we get lucky right before we get into fractions. I get a 0. Yes, so this one does work. Again, you can check with synthetic division. There is a quick way to do this, and I teach this in my calculus courses. The quick way to do it, if you graph it, and then you use a table. So putting into y equals to in your graph, and then how do you use the table? What you want to do is go into your table settings, which is the second window, and you want to make sure it looks like this, the table setup. It doesn't matter what's in the beginning, but the independent value, highlight the ask and click enter. Do not change the dependent value because they'll be calculated for us. Once you do that, then usually your calculator will save the setting. You don't need to do it again. So again, it's a second window. It's right next to the y equals to, but you have to press on second first. Once you do this, then you go into second graph and basically put in those values, and you'll have the y values very quickly. Or you can just plug them in. May not be that long to do. So if it's -2, let's actually do the synthetic division, and hopefully get 0 as the remainder, which is as it should. And so how do we do this? Again, we copy the leading term, 6. Then we multiply by -2, we get -12. Again, we add here. Let me write a little plus. Okay, so 13 plus -12, we get +1. Multiply with -2. Again, we add them. 1 plus -2 gives us -1. And then finally, -2 times -1, we get +2. And we get 0 for the remainder. So what is the remaining polynomial? Again, remember how you can start with a constant. It's -1 plus 1x plus 6x squared. Or basically 6x squared plus x minus 1. So we can try to factor it or use a quadratic formula. Okay, if you forget. So I think this was not too bad to factor. I tried with 3x on the 2x. And then I tried with 1 and -1. You know how you can multiply it out and check. And once you have the factored version, you can set them both factors equal to 0, and you'll find the remaining zeros. All right, so here's all the zeros. And the degree 3 polynomial should not have more than 3 zeros, which we'll find out. So these are all the zeros that we have. We'll find that out in the next section. And that's it. So do use graphing calculator /table. If you have questions, I can record a video on that. If this original polynomial is degree 4 or higher, then we may need to use rational zeros test twice to get it down to degree 3. Then we use it one more time, then get it down to degree 2. So you'll notice this method is not fast by any means. So if you can use graphing calculator, but even with graphing calculator, sometimes it's hard to approximate the zeros, especially if they're complicated fractions. So it's a useful method, but it's not necessarily fast. But you can use this method to find zeros even if they're not all rational. So like we'll do this with imaginary zeros in the next section. And I think for the rest, it's basically just practice with possible zeros, so it works the same way. I think this is the last example that we're going to do. So this one was not too bad because we had the constant constant term was 3, so you only get a couple of factors there. And the leading coefficient was 1, so literally we're just going to get integers here. That's nice when it works out that way. So here's our possibilities. Even for this simple example, you still have 4 possibilities, plus or minus 1 and plus or minus 3. Again, I just plugged them in. In the polynomial, I found -1. It gives us a 0, so that's our 0. Do the synthetic division, which you could have started with. And I find that the depressed equation is x squared minus 8x plus 3. So we can factor it. And here's what it looks like. Okay. We didn't really even do the factor. I'm going to basically just put it together. Can you factor x squared minus 8x plus 3? It's not factorable, but we can use quadratic formula. Okay, so if you remember, it's -b, which becomes positive 8 in this case, plus or minus b squared, which is 64, minus 4ac, 4 times 1 times 3. So I get 64 minus 12, we get 52, which actually is 4 times 13, so 2 can come out. And notice how we can cancel. Here, 8 divided by 2 is 4, and then the 2 should cancel out, just leaving it with radical 13. So in this case, we did have a couple of real zeros. But notice how we started with rational zeros, and then we ended up factoring it completely with quadratic formula. And that's it.